So we've already seen how we can form bromohydrins like this. So if I take an alkene, cyclic or not, any alkene with bromine, dibromine, and water will open up to give this, again, where my nucleophile ends up opening the bromonium ion at the more substituted end. What can I do with these things? One kind of cool thing we can do with them is treat them with base. So any old base, not any old base, but let's give it sodium hydroxide. That's probably good enough, right? So the most acidic proton in this molecule is here. So I'd get O minus. And if I draw it like this, you can maybe see where I'm going, right? So I've got now a very good nucleophile here. I've got a leaving group here. It's easy for me to get backside to it like that. And so that's going to form a ring. Sometimes we get tripped up by this, but remember, when we have a strong nucleophile and a strong electrophile in the same molecule, we can get cyclic compounds, right? So, or sometimes even if we have a cation, for instance, if we have a really strong of one and a weak the other, it can go. But this is a great example of an intramolecular SN2 reaction, right? So again, to draw it in 2D form, this is an epoxide. We talked about this very briefly in Organic 1, but these epoxides are really nice electrophiles themselves for further reactions. So if I give it some nucleophile, let's say a zid N3 minus, a zid, this will do a classic SN2 reaction, stereospecific at the less hindered side. You might be thinking, didn't we just learn all this loose SN2 from the bromonium ion? Well, that was when we had a positive charge on that bromonium ion. And not to complicate things, but if this had a positive charge, if we were doing this in strong acid, then yes, we would see similar reactivity. We would see the loose SN2 if this were protonated. But since this is not protonated, there's not a lot of positive charge. This is just going to be a typical SN2 reaction, reacting at the less substituted end. And that's what we'll focus on. So again, I'm breaking this bond here, right? This bond stays the same. And this bond is now inverted. Okay. So again, epoxides are really nice electrophiles. Here, this is essentially a way for us to go from an alkene to a di-substituted molecule in 2 steps. First to the epoxide, and then opening up. Epoxides are great because the reaction is stereospecific and regiospecific. I know it will attack there. I know it will attack with that stereochemistry. Pretty awesome. Epoxides are really useful. That last synthesis I showed you was an okay way to get them, but it was 2 steps. And we're going to use epoxides in the lab enough where it would be nice if there was a convenient way to get there in 1 step. So I'm going to show you this one other way to get there. I'm not going to give you kind of 10 ways to do every reaction that we study in this course, but I think this is useful enough to cover here. So this is MCPBA, metachloroperbenzoic acid. So it looks kind of like chlorobenzoic acid, but notice it's got 2 oxygens here. So it's almost like a peroxy acid. So this is a peroxybenzoic acid, metachloroperoxybenzoic acid. Okay. So I've kind of drawn it weird to prove a point. When this angle bends back like that, it's almost like there's going to be a little bit of attraction there, which is going to want to squeeze out this oxygen, right? And so this is a 1-step concerted reaction where we can kind of picture just the alkene going out to grab it, and then the the arrows kind of going like that. If these look like weird arrows, I agree. The transition state for this reaction sort of looks like a bow tie. So this is a concerted reaction. All the bonds are moving around at once. Frankly, our arrow structure kind of breaks down. But what we're seeing here is the transfer of this oxygen atom over here. So this is a one-step reaction to go directly from an alkene to an epoxide. If you're wondering why the chlorine and why the aromatic ring over here, it's mostly for practicality. So you can do this reaction with like peroxyformic acid or peroxyacetic acid. It works just fine, but those smaller peroxy acids are very explosive and hard to keep around. I myself think I was injured because of a little bit of formation with peroxy acid. And 19 stitches later, I like MCPBA better because this is a white crystalline compound. We've got some in the freezer right now. Really easy to weigh out, really easy to use. So this is kind of the much more common way to get at epoxides, a very, very useful synthetic intermediate.